Hi, my name is Steven, and I'm currently an intern at Tesla working on Dojo, and I help develop our new functional simulator to emulate Dojo D1 and D2 hardware. And I'm currently a software engineering at the University of Waterloo, so I come from Canada. And in the past, I was working at NVIDIA on their robotics team, where I got a pretty good introduction to, hardware acceleration running low-level C++, and I have very strong interest in robotics. And yeah, very very excited to interview for Autopilot. This has been a goal of mine since I guess entering university. I want to make. I just want to work on robotics and work on Optimus and work on Tesla's FSD. Okay, so tell me about some of the harder problems that you worked on. Sure, I can do that. So I guess I can tell you about um, what I'm working on recently at Tesla and some of the hard problems I had to deal with. So we're working on this new functional simulator. It's going to be, so there's we have existing simulators, but they're extremely slow. Um, they can only run a few hundred instructions at a second, whereas ours can hopefully do hundreds of thousands or 100x improvement. Um, the way we do that is by allowing it to scale, you know, multi-thread to be the multi-thread. And one of the big bottlenecks was actually their matrix multiplication implementations. So what I did was for the first month implement a new floating point library that enables vectored that calls vectored instructions under the hood. So what happens? So Dojo is its own hardware, right, and then its own instruction set runs super duper fast. But before the hardware comes out, we want to have a simulator to, um, you know, test to run to test behavior of software that we write for it. And previously, it was very very slow to run. But you'd expect simulators to be slow. But we wanted to, I guess, speed this up by quite a lot. So this new floating library actually is able to make use of vectored instructions. So we run on x86, but on x86 machines, I think we have a AMD Neon for AMD Neon, an ARM Neon, ARM Neon, a Zen. Or so we have, I think, AMD CPUs on our machines, and these AMD CPUs can support some D instructions. So these are special vectored instructions that use vector registers. And what that means is that when you do a for loop, so for like say for I in range 16, and you add two numbers together, instead of your compiler compiling it to a for loop and calling an instruction 16 times, what you can do is simply do a load into your vector register, call a SIMD instruction which will do this, um, you know, in one instruction, and that will save you a lot of time. Um, and currently we have it for AVX 512, which so these are 512-bit vector registers, and it can also generalize to 512 vector registers. And the reason it's able to be vectorized is because in the old code there was a lot of branching, a lot of complexity. It was using like global variables for like a format table that will tell you the bias. So instead you replace that with static const expr values, and those will just be inlined into the function. Like the function itself is inlined as well. And then when we have like a vectored call, you can you specify with like the restrict flagged and then that will tell the compiler that this is a pointer that will stay fixed, it will not move, and it will enable the compiler to do some optimization. And then we actually check this after the code gets compiled and see that the instructions are properly vectorized, and we have benchmarks, and we have testing. And I guess the interesting part was, our difficult challenge was actually getting the performance down while ensuring correctness. So testing, FP8. So we have also all these formats, all these operations, and it just grows combinatorically like a lot. So one is getting the implementation down correct, two, getting it fast while also ensuring its correctness, and then integrating all of that into our functional simulator. So I guess I got a pretty good understanding of how floating point. I should have a pretty good understanding of how floating points work. So there's some nuances like floating point 8 in D1 and D2 has slightly different behaviors. Specifically, for example, how the NaN works. So we have like 3 kinds of NaNs. We have like the canonical NaN. We just have like no NaNs, or I think 3 types like NaNs. We have like in D2 FP8s have a reserved NaN, which is D0, the negative 0. So if it's 1 and then a bunch of zeros, that usually is the sign 0. But for FP8s, we don't have a sign 0 because that number will be used as a NaN. So you have these edge cases. And then there's also different rounding modes. You can have a truncation, or you can have rounding, and then you can also have stochastic rounding, which like eliminates bias. So the idea is, imagine like you have some number 1.5, and that gets rounded, always gets rounded to 2, or like 1.9 gets rounded to 2, right? It rounds up. But if you that introduces bias into your system, right? So let's say the average value you feed is always 1.9, it always gets truncated up to 2. So you're going to have a bias of 0.1. So the way you get around this, really what you want to happen is when you do a conversion point 1.9 to 2, or actually, yeah, you want it to be 90% of the time it will round up, and then 10% of the time it will round down. Is that right? Yeah, I think so, right? And then, so that's 90.9 times 2 plus 0.1 times 1, and then that's 1.9. And so what you do is you like feed in this random register, and then for all the bits you get truncated, you just add it, and that is equivalent to stochastically rounding. But there's also edge cases when it comes to subnormals. Subnormals are, I guess, is when the exponent is all zeros and your mantissa is going to be. So can you describe to me a bit more about like how any of these work? I mean, I think like empirically it's not too difficult, all right? So for example, for conversion, so your source format and your destination format have different exponents biases. So first of all, you just go from your source exponent to your destination exponent. And then if you're going from a shorter to longer format, it's relatively straightforward. You just shift your mantissa to align it to your destination by some value, and then just check that your exponent is bounded. Like if it's too big to be represented in your target type, then you will do infinity. But there's also a case of where you do the shift, and then your exponent will be like negative, in which case you'll try to represent it as a subnormal. And then if it's not possible, then you return 0. And then, so there's edge cases like subnormals. There's edge cases where after you round, you might like have an extra decimal, and then you need to shift your exponent again. So you need to decrease the exponent, or sorry, your mantissa will be too big. So you're going to shift your mantissa, and then you're going to increase your exponent. So a shift of 1 to the right is essentially the division by 2. And then, do you know why floating points are used? Yeah, floating points are used because they have a they have a higher dynamic range, right? So like, if you had 8 bits, you can only represent numbers from minus, or it's like from 0 to 1, or from minus 2 to the 7 to 2 to the 7. Is that right? You have, well, you have 7 bits that you can use for the number. So that's the maximum number you can for that is 2 to the 7 minus 1. And then you can have sign, right? The sign bit. So it's like minus 2 to the 7 minus 1 to plus 2 to the 7 minus 1. So that's for integers and it's fixed. But if you have now use some of these for exponents, and the exponent it's going to be, the number will be 2 to the exponent, then you're working with a wider dynamic range. Like the number of different numbers you can represent stays the same, but you can have a wider range, and that's more useful in machine learning where you want to retain, I guess, a wider spectrum of numbers. Yeah. Okay, cool. So can you tell me more about, do you know what the diamond problem is? The diamond problem is when we have object and A. So this A, you don't know if it comes from A or B. This problem comes up like when you have multiple inheritance. You can use like scope resolution to figure out if it's from class A from class B. But once, if those two classes actually inherit the field from some actual parent class, and that declares a field, you immediately will have a compilation error, because now if so A, B, C, D inherits from both B and A, and then those two have inherited from the same field. So now you go, D will try to inherit this field A, but it doesn't know if it came from B or C. That actually they both came from the parent D. So the compiler will not allow this. So rather what you need to do is decouple it. You have B inherit from A and C inherit from A. And then you can make use of scope resolution to figure out if it's impaired. Or you can use a virtual inheritance. Although when you call the constructor, the parent constructor gets called, or I guess memory gets allocated, parent constructor gets called, member initialization list runs, and then your constructing body runs. So those are usually the 4 steps, and then destructor is in the reverse order. And the reason it's an issue is because okay, let's study this. And when your constructor calls like this derived class doesn't know this field, and it's deriving it from both B and C, which both derive it from A. But then now, if your field A, you don't know if it actually came from your parents, B or C, right? Because both of them inherit from the same parent. So you can either have them, this fix to this is to have them both inherit, or like separate um, when you do d.a, you can use scope resolution to d.b scope. So there's going to actually be two copies of A. And it can get very confusing because the inheritor variable you inherit a variable, the character structure. Can't delete. Does delete on the destructor. So there's so what's going to happen is there's going to be two instances, or two. I'm confused in the diamond problem. There are two instances of A that is when we create D, an object of type D. But it's not too accurate. When you initialize B, that doesn't have a copy of A. Instead, just calls A's constructor. A's constructor, and then B, but it's all B. what happens private field of A when we create? Do they just never get instantiated? Do private fields like if you look at the memory layouts, but when you look at the actual memory layouts, those private fields, it's just enforced in code. The access, so so B data layout will include A, but it's just not accessible code. actually I need to know. Yeah, sure, we can talk about cameras. I guess cameras, the way you represent cameras is through the pinhole geometry model. So you have these points in 3D, right? And when you project them down into a 2D plane, what happens is you're sort of like collapsing all these the z coordinates from a camera's perspective. So cameras like this, where z is forward, right is, generally that's the convention. Well, there's z up and z forward, right? So usually in camera we would work with z forward because you have your x going horizontally and your y going downwards, and your z goes upwards. So you're essentially collapsing the z coordinate down, right? And you essentially, I guess the way this is represented is through the camera matrix. So specifically, the focal length will tell you how that is represented. So at some point in 3D, you project that onto some plane at a fixed distance, right? So that's your fx and fy. Wait, I'm confused now. Fx and fy. Or no stretching. some shearing. This first fast. Okay. And I guess it's implemented. You implement this by blocks that are we